7.2 Properties of Parallelograms. So starting off, we're going to start with the generic parallelogram. So down here we have a parallelogram. Remember that if you see these arrows, okay, the double arrow here and the double arrow means that these two sides are parallel, and then the single arrow with the single arrow means that these two sides are parallel. So a parallelogram is a quadrilateral with opposite sides parallel. Okay, now remember that a quadrilateral means any four-sided figure. So this is a four-sided figure with the opposite sides parallel. Now, on a parallelogram, we have a couple theorems. The first one is the opposite sides theorem, which says opposite, meaning sides that are across from one another, sides are congruent. So if you look at your picture, these are not arrows, these are little tick marks. So we know QR is the same length as PS, and QP is the same length as RS, kind of like a rectangle, except this is a slanted rectangle. Then we have the opposite angles theorem, which says opposite angles are congruent. So I know that angle Q, which is opposite angle S, are the same measure. So if I were to say this is 100 degrees, then I would know this is 100 degrees. If I were to say this is like 80 degrees, then I would know that this is 80 degrees. We also have the consecutive angles theorem, which says consecutive, which I'm going to put next to, okay, angles that are like next to each other or in a row. Angles are supplementary, okay, which means they add to 180 degrees. So let's say I said that this x degrees angle S was 100 degrees, then I would know the angle next to him is 80 degrees. I could also go this way next to, and then this would also be 80 degrees, and then I could use my opposite angles. So opposite angles 80, 80, 100, 100, and then while we're talking about it, if I add up all four angles in any quadrilateral, specifically here a parallelogram, they're all going to add to 360 degrees. Something to keep in mind. And then the last theorem we're going to work with today is the diagonals theorem. So a diagonal kind of like goes from opposite angle to opposite angle. So diagonals bisect each other. Now keep in mind that bisect means to cut in half. So right here at M, which is where they intersect, we can say that QM is congruent to MS, and we could also say that PM is congruent to MR. Okay, so kind of you got your longer one is cut in half, your shorter one is cut in half. That's what we mean by bisect. Now, before we use these theorems, I am going to make you prove two of them. So the first one we're going to prove is the opposite sides theorem. Now, keep in mind that the opposite sides theorem says that QR is congruent to PS, and it also says that QP is congruent to RS. But if you look at what we're trying to prove that theorem so that in the future we can just use it. In order to do this, we're going to use a two-column proof. We're going to set up our work. We're going to set up our reasons. And all that we're given here is that PQRS is a parallelogram. So number one, PQRS is a parallelogram. And that is our given. Now, if we know it's a parallelogram and we look at our figure over here, we know that QR is parallel to PS, and we know that QP is parallel to RS. So they're never going to touch. So we have parallel lines. We are trying to prove that not only are they parallel, but that they're also congruent, so that down the road we can just use the opposite sides theorem in our proof, and we don't have to go about proving it. Now, the way I'm going to do this, step 2, is you notice that QS has already been drawn for us, which kind of takes our parallelogram and it cuts it into 2 different triangles. I'm going to try to prove that these 2 triangles, the one over here and the one over here, are congruent, because if I have 2 congruent triangles, then I know the sides of the triangles are the same length. Okay, so the first thing I'm going to look at is I'm going to look at the fact that this is a parallelogram, and I know that this guy is parallel to this guy, and I have 2 parallel lines cut by a transversal. If I have 2 parallel lines cut by a transversal, then I know this angle and this angle, which are alternate interior angles, are congruent. So I'm going to say, first of all, angle RQS is congruent to angle, let's see, PSQ. And the reason I can say that is because the alternate interior angle theorem. So I know one of the angles is congruent. Now, the next thing I'm going to look at is I'm going to look at that line that was drawn from Q to S. So number 3, I'm going to say QS is congruent to QS. Right there. And the reason I can say that is because of the reflexive property. That's that one where you kind of like are looking in the mirror at yourself. The next thing I'm going to look at is I'm going to look at these 2 parallel lines. And I'm once again going to look at this transversal. And I'm going to look at this angle, which is kind of now caught between the purple, and this angle, which is like caught between the purple. And I'm going to say angle, let's see, is that a P? PQS is congruent to angle RSQ. And the reason I can say that is, once again, alternate interior angle theorem. And now I've stated that I have an angle, a side, and an angle, and I have an angle, a side, and an angle that are congruent. So in step 5, remember those triangles, the red one and the blue one I was trying to prove are congruent? I'm going to say triangle, and I'm going to start out here with R. RSQ is congruent to triangle. And if I started out here with R, I'm going to start out here with PQS. And the reason I'm allowed to say that is because of the angle side angle theorem. Now, I have 2 triangles that are congruent, which means all of their corresponding parts are also congruent. So I already know that QS and QS are congruent to each other because I set it up here in step 3. But now I can also say that PQ is congruent to RS. So step 6, PQ is congruent, or I could say equal, because it does say equal up here, to RS, comma. And at the same time, I'm going to say QR is congruent or equal to SP. And once again, I'm not going to get too crazy about congruent versus equal here. And the reason I can say that is because corresponding parts of congruent triangles are congruent. So if the two triangles are equal, then their sides are also the same length, and that's your proof. Now, moving forward, since you've proved that on a parallelogram, you don't have to prove that again. If you need to say that QR is congruent to PS and we know it's a parallelogram, we're just going to use the opposite sides theorem. The next one I'm going to have you prove is the diagonals theorem. Okay. And then again, once we prove this once, then I'm not going to make you prove it again. I'm just going to let you use it in a proof if you need it. So let's set this up and then we'll take a look. Work. Reasons. Number 1, we are given PQRS is a, and I'm going to abbreviate this time and put the symbol for parallelogram. And then we also know diagonals, PR, and QS intersect at point M. And that is our given. So we know that PQRS is a parallelogram. Because of that, I do know, just by the definition of a parallelogram, that we're talking about parallel lines here. Okay, we also know that the diagonals are going to intersect here at M. But what we're trying to prove is we're trying to prove that M bisects QS, meaning that this guy is equal to this guy, and PR is bisected right here. So we're trying to prove PM is equal to MR. Now, once again, I'm going to try to use congruent triangles in here somewhere. And really what I'm going to try to do is I'm going to prove that this triangle, or I'm going to try to prove that this triangle over here is the same as this triangle over here. Okay, now the first thing I'm going to start with, if I'm doing triangles, this one I'm going to try to use angle, side. So I'm going to try to get two angles that are congruent and then one side. So the first angle I'm going to try to prove is congruent is sitting right here. So I'm going to say angle QMP is congruent to angle, so QMP was this guy, is congruent to SMR. And the reason I can say that is because they're vertical. So that's the vertical angles theorem. Number 3. That's one angle. I'm trying to get two angles. So the next angle I'm going to try to get is I'm going to try to get this one and this one. The reason I can do that is because I know this is a parallelogram. So if it's a parallelogram, I've got parallel lines cut by a transversal. So just like our previous proof, those are alternate interior angles. So I can say PQS is congruent to angle RSQ. And the reason is alternate interior angle theorem. So I have an angle and an angle. Now I need a side. Well, if I'm looking at the red triangle and the green triangle, the side I'm going to use is I'm going to use this one and I'm going to use this one. So step 4, I'm going to say that PQ, the side, is congruent to RS, the side. And notice the difference. You say an angle with 3 letters versus a side is 2 letters. That's important. And the reason I can say that is because I know it's a parallelogram. That's the opposite sides theorem. And remember how we just proved the opposite sides theorem, and I said moving forward I'm just going to let you use the opposite sides theorem? Well, that's how we're going to use it. Now, I've got an angle, and a side. I've got an angle, and a side. So now I know that my two triangles are congruent. So step 5, I'm going to say that triangle, and I'm going to start over here with P, Q, M is congruent. So if I started with P, I'm going to start over here with R, S, M. And the reason I can say that is because of angle, angle, side. Now, once I have this red triangle, and I have this green triangle, and I know they're congruent, then I know different parts of the actual triangles are congruent. So specifically in step 6, I know that QM is going to be the same length as SM. So QM is congruent to SM, comma, and then I also know that PM is congruent to RM. So PM is congruent to RM. And the reason I can say that is because corresponding parts of congruent triangles are congruent. Now, if I look at what I'm trying to prove, it says prove that M bisects QS and PR. Well, think about this. If QM is the same as SM and PM is the same as RM, okay, and everything's kind of got an M in there, that's really what we've proved. We just haven't stated it that way. So in step 7, I'm going to say that M bisects QS and PR. And the reason I'm going to say that is by the definition of bisect. Okay, and the definition of bisect means I cut it in half. So if I look in step 6, QM is congruent to SM. Yeah, it cut it in half. M, that point, cut it in half. And then PM is congruent to RM. So M cut it in half. So if M cut these things in half, then I know it must bisect QS and PR. And again, that's the definition of bisect. Moving forward, now that you have proved the diagonals theorem, I'm not going to make you prove it again. You can just use it in a proof if you need it.